team. We're going to pick up from where I left off in class. So it's question 18 on your review, and I'm going to jump right in. I'll try not to make this too long, but if you notice any errors or run into any questions or would like anything explained a little more, feel free to send me an email. That's always an option. So let's jump into it. We're going to start with question 18. Hope you can see everything okay. We're jumping into the naming part. So they gave us the formula rather, CUF, and we're going to turn it into a name. So we'll ask our questions. Is it ionic or is it covalent? The first would be, okay, it's a metal and a non-metal, or something positive and something negative. Therefore, we would say that it is ionic. So we'll follow those rules for naming. Because it's ionic, we have a few follow-up questions. The first is there a transition metal? So copper is a transition metal. It's found in groups 3 through 12. Anywhere in that section, those metals are considered transition metals. And there are a couple of different options in terms of charge. So we're going to have to figure out the charge and add it in the name. So if you check out your periodic table, let's just put the charges that we know about first. Fluorine has a charge of 1-. Copper, there's 1 copper to balance out that charge. So it must be 1+. So when we name it, we'll say copper, and we'll put the charge in brackets in Roman numerals, 1 fluoride. Okay, 19. Oh, there's a second part to 18. Scrap that. SO2. Oh boy. SO2 is, we want to ask if it's ionic or is it covalent. You'll notice that there's no charge there. This looks suspiciously like a polyatomic ion, but it is not. There's no charge and there's no metal associated with it at the front. These are all nonmetals, the sulfur and the oxygen, both nonmetals. So this is a covalent compound. Important distinction between this and something like sulfate or sulfite, or sulfide is the sulfur by itself. Okay, so let's use our covalent naming rules to name this one. There's only 1 sulfur, and because it comes first, it doesn't get a prefix then. It doesn't get the mono sulfur, it's just sulfur. Sulfur, and there's 2 oxygens, so we'll put di for 2, and oxide, IDE ending. There, so sulfur dioxide. Okay, now on to 19. So we're still naming. The first one is CBr4. So our first question is that ionic or covalent? There's no metal in there, so we'll say it's covalent. And if it's covalent, we can use our prefixes to name it. So the first one, carbon, because there's only 1, and it's the first one, we won't give it the mono. And then 4, there's 4 bromines, so we're going to say tetra for 4, and bromide with that IDE ending. And we also, in number 19, want to name this one NaOH. So again, is it ionic or is it covalent? Well, there's a metal and some nonmetals, so we know it's ionic. And we want to ask about transition metals. Sodium is not a transition metal, so we don't have to worry about putting a charge in there or specifying charge. We know the charge of sodium because it's in group 1, it's going to be 1+. Also, we want to look now for, is there a polyatomic ion? So our 2 questions for ionic compounds, is there a transition metal and is there a polyatomic ion? So because here we find OH, this is a polyatomic ion on our list. Remember that list will appear at the top of your test. We're going to call this sodium, so we just name the metal. And then name the polyatomic ion in this case, which is hydroxide. And that's it. Number 20. We're naming Cu2O and also CuSO3. Okay, so let's start with the first one here. We've got some copper and some oxygen. We want to know, is it ionic or is it covalent? Well, there's a metal in there, so it's ionic, metal and a nonmetal. And then we want to ask the follow-up questions when it's ionic. So is there a transition metal? So as we were seeing in number 18, copper is a transition metal. And there are a couple of different options, so we're going to have to specify the charge again, of course. We also want to look for polyatomic ions, but because there's only 2 different types of atoms here, there cannot be a polyatomic ion. There has to be at least 3 types of atoms involved for it to be a polyatomic ion, so it's not the case for this one. Let's look at copper, and it will be O for oxide. And we have to specify the charge of copper, so let's figure that out. Oxygen, because of where it's placed on the periodic table, we know that it has a charge of 2-. Copper, it says there are 2 of them, so we can put these placeholders in. There's 2 coppers, and they have to add up to 2+. So the only real good option there is 1+, and 1+ makes 2+. So copper 1 oxide is our name. Let's look at the next one, which is CuSO3. So our first question, is it ionic or covalent? Well, this one again has copper in it. It's got a metal and some nonmetals, so this is ionic. We can look for a polyatomic ion. We found one in SO3. This is not on your list. SO4 is on your list, which is sulfate. This has 1 less oxygen, so this is sulfite. This is copper. Sulfite, IT ending. And we want to look for a transition metal. So copper is a transition metal. We're going to have to put in the charge. SO4 is 2-, and so is SO3. They're always the same, the 8 version and the IT version. They have the same charge, in this case 2-. We have 1 copper in this case to balance out all of that. So it has to be 2+, because we have to balance out the 2-. So copper 2 sulfite. Okay. Let's look at number 21. We have MnS. So first question, is it ionic or covalent? Because of Mn, this is a transition metal. Because this is a metal, we know it's ionic. It's a transition metal, so you can say manganese. Something in the brackets, because we're going to have to specify the charge. And S for sulfide, IDE ending. Here, don't get confused with sulfate or sulfite, but this is sulfur by itself, sulfide. Okay, let's figure out what the charge of manganese is. Because sulfur has a charge of 2-, and there's only 1 manganese to balance that charge of 2-. This has to be 2+. Manganese 2 sulfide. Let's look at the next one. It says NH4, NO2. Now, when you get questions that have a lot of different elements in them, you might want to go looking for polyatomic ions immediately. Here, NH4 is ammonium, and NO2 is also on your polyatomic ions list as, well, NO3 is on the list, nitrate, so NO2 is nitrate. So this is ammonium nitrite, ITE. So when you see those polyatomic ions, you don't have to ask about the transition metal because there isn't one. It is ionic, and you can just plunk in the names of each of the polyatomic ions. 22. Name the following compounds again. We have iron and oxygen. Let's go through our questions. Is it ionic or is it covalent? There's a metal in there, so it must be ionic. So we'll write iron, and we'll write oxide, IDE. We also want to look, we might notice that there's no polyatomic ions because there's only 2 different kinds of atoms. We have to look at our metal and say, is it a transition metal? In this case, it is. So we will add our charge into the name. Again, that charge only belongs in the name. We don't have to write the charge in the formula because we can figure it out from looking at the formula. Here's how we do it. O is 2 minus. There's only 1 iron, and it has to balance out that 2 minus, so it's got to be 2 plus. So iron 2 oxide. Next, CaCO3. So here, again, with the questions, is it ionic or is it covalent? This one is ionic because there's a metal and some nonmetals. We notice that there's more than 2 types of atoms, so there is going to be a polyatomic ion. And we can look and say, calcium, okay, that is not a transition metal, so all we have to deal with is an ionic question with a polyatomic ion, no transition metal. We'll call it calcium. Don't have to worry about the charge. And then CO3 is on your list. It is called carbonate. ATE. There we have it. So, number 23 moves into turning names into formulas. So we've got hydrogen, sulfide. So here, hydrogen and sulfur. We want to look at the charges to make sure we have the right numbers of each. So sulfur, 2 minus, hydrogen, 1 plus. If those charges don't come to mind or looking at your periodic table, it's still a bit confusing. You'll want to make sure that's really solid before you write your test. Here we've got 2 minus and you want 1 plus. Well, you're going to need a little bit more positive charge to balance it out. So you need 2 hydrogens and 1 sulfur, so it becomes H2S. Okay, copper 1 chloride. Copper 1 chloride. So we'll start with Cu. Move this up here. Cu and chlorine is Cl. We have to balance the charges. Chlorine is 1 minus. Copper, we can look to the name. If we look at the periodic table, there's options and we won't know which one to use. So let's look in the name for the charge as 1. So 1 plus and 1 minus, we're in balance, so our formula becomes CuCl. Number 24. We have iron 3 oxide, iron 3 oxide, like so. Iron is Fe, oxygen is O. Now, we'll want to balance the charges. We have a metal and a non-metal, so that's going to be the case. Oxygen is 2 minus, and we need to know how many irons we need to balance that. Well, we already know from the name that the charge on iron is 3 plus, so let's make this 3 and this 2 balance out. So right now we don't have enough negative charge, add some more. Now we need some more positive, now we need some more negative, right until we get the same number, so 6 and 6. So then we can count up how many irons we needed. We needed 1 iron, 2 irons, Fe2, and 1, 2, 3 oxygens, Fe2O3. Okay, and let's look at the next one. I'll stick it in here. Ferrous oxide. So again, when we see that ferrous, it's going to be iron, Fe, and oxide is just O by itself. We know oxygen is 2 minus, and we need to know what the charge of this ferrous is. Because it's ferrous, it's 2 of us, the charge is going to be 2 plus. So Fe 2 plus and O 2 minus, our charges are in balance, and our formula becomes FeO. Don't forget we also have ferric, which is 3 plus, is the other option. Okay. Flipping the page over, I need one of those little chimes to tell you to turn the page. Maybe some of you will know what I'm talking about. Anyway, flipping over the page to number 25. You know, books on tape from when you were a kid. Anyway, write the chemical formulas for the following compounds. Aluminum nitrate, Al for aluminum. Nitrate is on your list of polyatomic ions. Don't forget to go and look at it. NO3. We have to balance those charges to make sure the right number of each is involved. Aluminum is 3 plus. NO3 or nitrate is 1 minus. That it will say it at the top of your test. We need to balance them out. We don't have enough negative charge. Let's go ahead and add some more until we have 3 plus and 3 minus total. We only needed 1 aluminum, but we needed 1, 2, 3 nitrates. So we'll put the nitrates in brackets and say we needed 3 of them so that our formula becomes AlNO3, 3. Okay. We also, I didn't write the name of that. Okay, so calcium hydroxide is our next one. Calcium is Ca, hydroxide is OH. We'll need to balance our charges. Ca is 2 plus, OH is 1 minus, so we'll need another OH so that we have 2 plus and a total of 2 minus. And because we needed 1 calcium, we don't need any subscript, but we need 2 OHs, so we'll put them in brackets and say we need 2 of those. So CaOH, the OH is in brackets with a 2. Okay, let's look at 26. Chemical formulas for sodium sulfite, ITE. Sodium is Na. Sulfate is SO4, so we can figure out that sulfite is SO3. This is a 2 minus. It'll say it on your list. Na is 1 plus because it's in group 1. And we'll need 2 of those to balance out the negative 2 charge there. So Na2SO3 becomes our formula. All right. We also have calcium sulfate. So Ca for calcium, SO4 for sulfate on our list. Ca is 2 plus, SO4 is 2 minus. The charges are in balance, so I can leave it as is, CaSO4. 27. Okay, write the chemical formulas for magnesium carbonate. Magnesium is Mg. Carbonate, CO3. Mg is 2 plus. CO3 is 2 minus. They are in balance, so my formula is MgCO3. Zinc hydroxide. Zinc hydroxide. Zinc is Zn. Hydroxide, don't get confused. It is not oxygen. It is not hydrogen. It is not on the periodic table. Hydroxide is a polyatomic ion that is OH. Zinc, I believe, is 2 plus. And so OH, it's 1 minus, and we'll need 2 of them to balance out that 2 plus. So ZnOH2. More chemical formulas. 28. Iron, 2 phosphate, iron is Fe. This 2 in the name indicates that the charge is 2 plus. Phosphate is PO4, and it's 3 minus. So we're going to have to balance those charges. We'll need 2 more of those and another one of those until we get 6 plus and 6 plus and 6 minus. So Fe3, that's a 3 I swear, PO4, and there needs to be 2 PO4s. Okay. Copper, 1. Fluorite, IT ending. So Cu for copper, it is 1 plus because the name says so. Chlorite is ClO. Okay, chlorate is on your list. So ClO2. Chlorate is ClO3, so chlorite will be ClO2. Its charge is 1 minus. Chlorite and chlorate have the same charge. So now we have 1 plus and 1 minus. We're in balance, so our formula stays the same, CuClO2. Onwards and upwards. 29. Okay. It says write the formulas for the following compounds: ammonium hydroxide. Okay, let's start with that one. Ammonium is NH4. It's on our list of polyatomic ions. Hydroxide is OH, also on our list. NH4 is 1 plus, OH is 1 minus, so that is our formula, NH4OH. Ammonium nitrite. Ammonium nitrite, ITE ending. So ammonium again is NH4. Nitrite, okay, well on your list it says nitrate is NO3, so nitrite must be NO2. NH4 is 1 plus, this 1 minus. We're in business. Okay, 30. Some good practice with combustion reactions. So it says write a balanced equation for the reaction of gasoline, which is C8H18, with oxygen gas, which you should automatically know when you see a fuel with C's and H's in it, and it's reacting with oxygen gas, O2. It's going to be a combustion reaction. So first it says write the balanced equation, so let's do that bit. When it's a combustion reaction, it always produces CO2 and H2O. We're always talking about complete combustion when we're doing these. I'll make the distinction later between complete and incomplete. So let's balance looking at our carbons first. So we have 8 carbons on the reactant side, 1 on the product side. So let's multiply the products by 8. And we have 18 hydrogens over here on the reactant side. Here we only have 2 on the product side, so we need to multiply this to get 18. So I'll put a 9 in front. For our oxygens, we now have 2 times 8 gives us 16 oxygens, plus 9 more gives us 25 oxygens. So we want to put 12.5 in there, but we can't. So we'll add a 1 in front over here just so that we can double everything easily, right? When we see that problem, if we've got an odd number of oxygens over here, oxygen is the only thing we have left to balance, and we just need to put a coefficient in here that gives us 25 or whatever odd number it may be. That's when we're going to double everything. So don't forget to double that first one. Then we'll double our 12.5 to get 25, and then we'll double our 8 to get 16, and double our 9 to get 18, and we should be all set. Notice there is no number we can divide evenly into all of these coefficients, so we know that we have the simplest balancing possible. So this was A, 30A. So B, this is combustion. It asks for the type of reaction. That's combustion. C says, where did the carbon in the CO2 come from? Came from the gasoline, right? This carbon used to be in this kind of configuration. When the reaction happened, it all broke down and it formed something new, which was CO2. D, which bonds have broken during the reaction? All bonds holding reactants together. They just break during the reaction. Which new bonds have formed? All bonds holding the products together. They are the ones that formed, right? So everything here had to break down, everything here had to come together. Okay, my little chimes, we're going to turn the page and go to our next question, which is number 31. It says, what do the electronegativities of calcium and chlorine tell us about the bonds formed between these elements? Now, I've used a different periodic table than the one that you have, so hopefully these numbers will line up. If the numbers aren't the same as the ones on your periodic table, just use the ones that you have, that's fine. But you'll still get the same idea. So, for number 31, we have calcium, which has an electronegativity value of 1. And we have chlorine, which has an electronegativity value of 3.16. So immediately it tells us that chlorine is better at pulling on electrons than calcium, because the electronegativity is their ability to pull in the electrons. When we do that subtraction, we get 2.16, which is bigger than 1.7. Therefore, this means they would form an ionic bond. Calcium would lose the tug of war for electrons. It would lose electrons to chlorine. Okay, and that's it for number 31. Let's go on to 32. Okay, why does solid sodium chloride not conduct electricity, whereas aqueous sodium chloride will conduct? Solid sodium chloride, NaCl, is stuck in a rigid crystal lattice, and ions cannot move to allow electricity or charge, however you want to think about it, to flow, to move, right? When NaCl is dissolved, the crystal lattice breaks down, and the ions can move in water, allowing electricity or charge to flow. Hopefully you can read that. Here it is. Number 33. So it asks, what happens in pure covalent bonding? Electrons are shared equally in impure covalent bonding. I think that's all you need there. Number 34. Use a Lewis structure to show the bonding in a molecule of oxygen gas. Okay, so the first thing we need to ask again about these Lewis structures is it ionic or is it covalent? So in O2, we only have non-metals, so this is a covalent kind of situation. So when we draw our Lewis structure, we have to remember that there's going to be some sharing. You have to go through that process. So for O2, let's start with our electron count. So each oxygen brings 6 electrons to the table, and there are 2 oxygens. So we have a total of 12 electrons to play with in our picture. Let's place the atoms on the page, and now we'll assume single bonds to start, and we can put everything in pairs because eventually all of the orbits will be full. Okay, so 2, 4, 6, 8, 10, 12. You might notice that even though we put all of our electrons on the page, we still ran out, right? This oxygen needs another pair here, or needs access to another pair somehow. So what we're going to do is we're going to take some of these electrons and share them with that other oxygen. So it ends up looking like this. Double bond. Right? And because they asked for the Lewis structure, we will take these electrons and turn them into sticks because they're the bonding electrons. So here we go. There's a double bond in there, and the non-bonding electrons go in our picture as well. So that shows the bonds in our molecule of oxygen gas. 35 asks, why do covalent compounds such as sugar not conduct electricity even when dissolved in water or melted? So electricity is moving charge, and molecules like sugar do not break into ions when dissolved in water. So because sugar is not an ionic compound, it doesn't break into ions when we put it in water. It then doesn't have ions that are free to move and be electricity. That's not a thing that sugar can do because it doesn't produce ions. All right. 36 says, using water as an example, distinguish between intramolecular and intermolecular forces. So here is water. There's a Lewis structure for water. It's that bent shape. Oxygen is bound to hydrogens, and then it has those extra electrons around it. Now, oxygen is slightly negative. It's the electron hog. It's got more pull on its electrons, a higher electronegativity, so the electrons spend more time around oxygen. Hydrogen is slightly positive, so the electrons that are kind of being shared between oxygen and hydrogen are spending more time around the oxygen, leaving the hydrogen kind of deficient sometimes. So we have this polar molecule that's kind of set up like this. Now, this here is an intramolecular molecular force, aka a bond. Intermolecular forces, on the other hand, are what stick molecules together. So when another water comes along, it will have a hydrogen end that is also slightly positive, and an oxygen end that is also slightly negative. The positive end of one molecule will interact with the negative end of the other molecule. And just to represent that interaction or that attraction between the molecules, we often see these dashed lines. Doesn't matter how many dashes, but the dashes between say they're attracting. And there's a special name for this. There's two names, I guess. This is called the kind of intermolecular force, which is this, intermolecular force, is called a dipole attraction. And because it's between oxygen and hydrogen, it's a special kind that's even a little bit stronger that we call hydrogen bonding. Now this part about what kind of force is a little bit extra to the question, but I wanted to add it just to give you a little reminder in there. So all you really need is this part and an explanation. Next, we're looking at which of the following is isoelectronic with argon. And it says oxygen, an oxygen ion, a chlorine ion, neon, or potassium. So here we want to know which is isoelectronic, which means which has the same number of electrons as argon. When oxygen gains 2 electrons, it now has the same number of electrons as neon, so that doesn't work. If you look at chlorine, it gains 1 electron, and it does become isoelectronic with argon. So for 37, B, chlorine is definitely, the chlorine ion, chloride, is definitely one of them. Neon does not have the same number of electrons as argon, so that's out. Potassium is over here, and potassium is a metal, so it loses an electron. It had 19, right? 1 in its valence shell, and then when it loses it, it has 18, the same number as argon. So also potassium, D for potassium, is isoelectronic with argon. So chlorine 1 minus, and also potassium 1 plus. So let's flip the page over to number 38. 38 says, state the law of conservation of mass. What does it have to do with balancing equations? So the law of conservation of mass says that the mass of the reactants must equal the mass of the products. And this is why we balance equations. So we balance equations so that we have the same number of each atom on the reactant side as we have on the product side when we add the masses of atoms on the reactant side, we will find that this mass is equal to the sum of the masses of the atoms on the product side. There's probably an easier, maybe not easier, but a more succinct way of saying that, but hopefully that's clear. If you have any questions, email me. Okay, let's look at number 39. It says state the law, 39. Describe how electrons are shared unequally in a molecule of water. Okay, so we have our water. We draw our Lewis structure, and here's our electrons and our bonds. With our water being slightly negative and our hydrogen being slightly positive. So because oxygen pulls harder on electrons, they spend more time around oxygen, leaving hydrogen slightly positive and oxygen slightly negative. That's it. That's all. 40. Why do water droplets on a window pane stick together? Water is polar. Thus, the molecules have high, scratch that, intermolecular forces. The H2Os stick together to form droplets. Yeah. Okay. 41. In CF4, which end of the CF bond is slightly positive? Okay, so we need to look up our electronegativities. When we compare electronegativities of carbon to fluorine, we find that carbon has an electronegativity of 2.55, fluorine has one of 3.98, and so that means that fluorine is the bigger electron hog. It's better at pulling on electrons than carbon is. So that means that this is going to have extra electrons some of the time, which would leave the carbon being slightly positive. So for 41, carbon would be slightly positive. 42. Is the molecule CO2 polar or nonpolar? Explain. So when we're looking at is a molecule polar or nonpolar, we have two criteria. One is it has to be an asymmetrical shape. The other is it has to have polar bonds. So we have to check the difference in electronegativity, right? Do the math, draw the molecule, see what you find. So for CO2, let's draw it first and see what we know about asymmetry. So when we're drawing a covalent compound like this one, we want to add up all of our electrons. Carbon comes to the table with 4 electrons, and there's only 1 carbon. Oxygen comes to the table with 6, and there are 2 oxygens. So when we add all of that up, 6 times 2 is 12, plus 4 gives us 16 electrons total. And for CO2, we can put our carbon in the middle and our oxygens around it. That's typically how it goes if you have a bunch of something connected with only one of something else. So let's start putting on our 16 electrons. 2, 4, 6, 8, 10, 12. And now if I add the next ones, we're going to run out, so they better be shared. You've seen this one a couple of times, so I'll trust that you've got it. We'll do a bit of shuffling of those electrons, and here we go. So we've got oxygen, 2, 4, 6, 8, other oxygen, 2, 4, 6, 8, and carbon in the middle, 2, 4, 6, 8. So we've got everybody being stable with their 8 electrons. We should only have 16 in the picture, 2, 4, 6, 8, 10, 12, 14, 16. Now when you build this in the lab, you would have seen that this makes a shape that kind of goes like that and like that, which is actually a linear configuration. So if it's linear, the electrons are being pulled to one side and to the other side, right? But not in a way that leads to one side of the molecule having that positive and one side negative. They just pull the electrons out, right? Which doesn't really get us that asymmetry. So we have failed this first test. If you want to do electronegativity, you can, but once you know that shape is not asymmetrical, we failed the test, therefore it must be a non-polar molecule. Okay. Okay. Moving right along. Number 43. Do nonpolar molecules generally have lower or higher boiling points than polar molecules, and why? So polar molecules have a positive end and a negative end, and they stick to their neighbors like so, kind of like magnets with north and south. Positive and negative sticks together. When we've got nonpolar molecules, they don't stick together. There's no attraction between them. They just not paying any attention to each other. So it takes a lot, oops, that's supposed to be 2 words, a lot of heat energy, whichever you want to think about it, to overcome this attraction to allow the molecules to, let's say, escape as a gas, right? They'll have to break that association and fly off into the atmosphere as a gas. So it takes a lot of energy to do that. Therefore, they have high melting and boiling points. So here they were asking us about boiling point. So we'll say high boiling points. Compared to these, and these are polar, these are non-polar. So, no attraction, therefore low amount of heat or energy, heat energy. It only takes a little bit, right? As low amount of heat or energy to allow these molecules to escape as a gas. Therefore, low boiling points. Cool. 44. Complete the word equation and write the balanced equation for this single displacement reaction. Okay, it's a single displacement. We have magnesium, and don't forget about the word equation, right? Magnesium and silver nitrate. And we want to know, will this magnesium come in and kick out, so magnesium is a metal, so it's going to kick out the metal, which is silver, to make silver be all by its lonesome and magnesium nitrate. Before we go any further, you'll want to check to see if this is something that actually can happen, if magnesium is strong enough to kick out that silver. Here's an activity series. So we want to compare our magnesium and our silver. So you'll notice that magnesium is here and silver is down here. You should have your copy and it'll be ready for the test, ready to bring in. But for now we can take a look at this one. It works the same way as the higher up on the list, the better it is at reacting. So we have magnesium that is above silver. So it's better at being in a compound than silver is. And if you look at the situation that we have, magnesium is not in a compound, but it's better at being in one. So this is going to happen, right? It's so good at being in a compound, it's going to kick that silver out and form magnesium nitrate and leave silver all by its lonesome. So we are in business here. So magnesium, let's turn this into some formulas. Magnesium is Mg, and silver nitrate, silver is Ag, nitrate NO3. Silver is 1 plus, nitrate is 1 minus, so we're all good. Then we have silver, Ag, all by itself, and magnesium, Mg, with the nitrate, NO3. Magnesium is 2 plus, where nitrate is 1 minus, so we'll need 2 nitrates to balance that out. Now we have our skeleton equation. We need to add some coefficients, balance the overall equation. So magnesium, we have 1 over here and 1 over here, so we're okay. Silver, we have 1 on the reactant side, 1 on the product side, we're all right. Let's look at nitrogen, or we could look at NO3 altogether. We have 1 nitrogen over here and 2 over here, so we are not in balance. Let's put a 2 in front to balance that out. So now we have 2 and 2. Right, so and there's 1 in each group. There's 2 groups. There's 2 from over here. And now there's 2 of these compounds, 2 nitrogens. Let's look at oxygen. Oxygen, here we have 3 in this compound times 2 makes 6. And over here we have 3 times 2 gives us 6, so that's in balance. Now that we've gone through all of our atoms involved, let's do that one last check. Magnesium is 1, magnesium is 1. We're okay. look what happened to our silver. We have 2 silvers over here now and only 1 over here. So let's put a 2 in front to balance those out. And now we're okay again. Nitrogen, there's 2 and there's 2 over here, so we're set. Oxygen, 3 times 2 is 6 and 3 times 2 is 6, so we're all set. So there is a single displacement reaction with the word equation completed, the skeleton equation written out, and then balanced. Okay, let's flip over the page to our last and final one. Last final page. So number 45 says complete the word equation and write the balanced equation for this decomposition reaction. Okay, I will kind of add a little caveat here. This is nice to think about as a practice question or as an extension of your knowledge, but this is not, I repeat, not going to be on your test. When we have decomposition reactions, we don't always know what the products will be before we know about a bunch of different conditions in the lab. So although this is hydrogen chloride, H and Cl, and we might take a wild guess that it's going to break up into hydrogen and chlorine, we don't necessarily know exactly what compounds will form. So this is not really a question that we can ask you. But let's do it anyway. So hydrogen is 1 plus, chlorine is 1 minus. When it breaks down, we can assume, if this is a decomposition reaction, that hydrogen and chlorine will then be on their own. These are both on our list of diatomic molecules, so this becomes H2 and Cl2. So here's our skeleton equation, and it says for us to write the word equation and the balanced equation. I guess I kind of jumped the gun to the formulas here, but that's okay. Let's balance this first, then we'll come back to the words. So 2 of each of this hydrogen and chlorine. So if you look at hydrogen first, there's 1 over here, 2 over here. So let's add a 2 in the front to balance those hydrogens. Now we've got 2 chlorines on our reactant side and 2 on our product side. So that's balanced. We can do our last check. Hydrogen, oh, my marker's running out. 2 and 2, and our chlorine, 2 and 2. We're all set. So let's add the word equation in here. So hydrogen chloride, IDE ending, because chlorine is all by itself, and it's breaking down into hydrogen and chlorine. Notice it's chlorine, not chloride, hydrogen, not hydride, because when they're all by themselves, they just get the name that whatever it says on the periodic table. Okay, so that's number 45. Let's look at 46. Complete the word equation and write the balanced equation for this double displacement reaction. So we're going to need some space. Here's barium chloride plus sodium carbonate. And it's a double displacement reaction, so we know that they're going to trade places and make ionic compounds. So this barium isn't going to be with this negative chloride anymore. Barium is going to be with the negative one over here, which is the carbonate. So barium carbonate. There we are. And sodium is going to get a new partner. The only one that's left over now, chloride. So we have a word equation now. Let's turn it into some formulas. So barium is Ba, chlorine is Cl, barium is 2 plus, chlorine is 1 minus. So we'll balance those charges and it becomes BaCl2. Sodium carbonate, sodium is Na, carbonate is CO3, CO3 2 minus, Na is 1 plus. So we'll need 2 of those, put 2 in there to balance those charges. barium carbonate, BaCO3. Ba is 2 plus, CO3 is 2 minus, so we're good. Sodium, Na, chlorine, Cl, 1 plus, 1 minus, we're also in balance. So now that we've made all of our ionic compounds involved in this reaction, we've got our skeleton equation, right? We need to balance it. So let's look at barium. We have 1 barium here and 1 over here. We're good. Chlorine, 2 over here and only 1 on the other side. So let's put a 2 here to balance them out. So now we have 2 and 2. We have 2 sodiums here on the reactant side. And now because of this 2, we have 2 sodiums on our product side. So 2 and 2. Carbon, 1 over here and 1 over there. We're all set. Oxygen, 3 and 3. So we'll do our last check. Barium, 1 and 1. Chlorine, 2 and 2. Sodium, 2 and 2. Carbon, 1 and 1. Oxygen, 3 and 3. So we're all set. We just needed that 2 and we're all balanced. 47. Write the balanced equation for this synthesis reaction. So it says calcium reacts with nitrogen. Calcium reacts with nitrogen to produce calcium nitride. IDE ending, so you know nitrogen is by itself. Now, nitrogen, when by itself, it's one of those diatomic molecules, so we'll put a 2 there. And over here, when we're making calcium nitride, we better balance those charges, Ca2 plus with N3 minus. So here we go, 6 and 6, Ca3 and 2. Right? So now that we have the balanced equation, now that we have the skeleton equation rather, we can balance it. So we have calcium, which is only 1 over here and 3 on the other side, so we'll put a 3 to make 3 and 3. Nitrogen, we have 2 over here and 2 on the other side, 2 and 2, and we're balanced. So one last check, 3 and 3, and 2 and 2. And it's only asking for the equation, so we're done with 47. 48. Would mercury displace lead in this reaction? So we have Hg plus PbNO3 gives us HgNO3 plus Pd. So we have to compare them again, and so for that we'll need our activity series of metals. Here's our activity series. We're comparing metals, Hg, which is mercury, which is way down at the bottom, and we're comparing it to lead, which is a little further up. So lead is better at being in a compound. And if we go back, lead is already in our compound. So nothing is going to happen here. No reaction. It does not take place. Mercury is not strong enough to kick lead out of this compound. Okay. So, no. Is really all I need there. So let's look at 49, which is some balancing. So balance these equations and state the type of reaction that is occurring. So we have Ca, OH, and there's 2, plus Na3, PO4, Ca3, PO4, 2, and NaOH. Okay. So when I look at this, I notice there's metal, non-metal, metal, non-metal, metal, non-metal, metal, non-metal. These are all ionic compounds. And we can see that they switched partners. So now that calcium had hydroxide as its partner, but it gets a new negative partner, PO4. Here it is. This is, maybe not, maybe just, this is a double displacement. And we want to balance it. Let's look at our calcium first. We have 1 over here and 3 over here. So let's put a 3 in front. 3 and 3. Oxygen looks fairly complicated. Let's leave it to the end. Well, I think our hydrogen looks a little better. So we've got 1 hydrogen in OH. We've got 2 OHs, so 2 times 3 gives us 6 hydrogens on the reactant side. Over here on the product side, we only have 1, so let's put a 6 in front here. It's got a little messy, but you see what I mean, I hope. So now that we have hydrogen, we have 6 and 6. Let's look at sodium. We have 3 over here and 6 over here. So let's put a 2 in front here to balance that out. So now we've got 6 and 6. And if you look at phosphorus, we have 2 of them here, and we have, these are getting a little smudgy. That is a 2, PO4 2. So there are 2 and 2 phosphorus atoms. Let's look at our oxygen as our final step. Here, oxygen times 2 times 3 gives us 6 oxygens, plus our oxygens from over here. So 4 times 2 is 8. So 6 and 8 give us 14 oxygens altogether. Over here, we have 4 by 2 is 8, plus 6 more gives us 14 oxygens as well. So it looks like we're balanced, but let's do our last check. 3 calciums, 3 calciums. 6 hydrogens, 6 hydrogens. 6 sodiums, 6 sodiums, 2 phosphorus, 2 phosphorus, and 6 plus 8 oxygens gives us 14, and 8 plus 6 more oxygens gives us 14, so we're all set. This was 49A, so let's look at 49B. Fe plus HCl gives us FeCl2 plus H2. Let's balance that. We have iron, 1 over here and 1 over there. We're good. Hydrogen, we have 1 here and 2 over here, so let's double this guy for 2 and 2. Chlorine, there's 2 here and 2 over here. 2 and 2. Do our one last check. 1 and 1 iron, 2 and 2 hydrogens, 2 and 2 chlorines. What kind of reaction is this? Iron took the place of hydrogen. So this is a single displacement reaction, sometimes called a single replacement reaction. We can tell also because there's something all by its lonesome, and then an ionic compound, and then there's a bit of trading going on, right? Okay, let's look at 49C. NaCl and A plus Cl2. So let's get at our balancing. 1, 1 for Na. Cl, there's 2 over here and only 1 over there, so let's put a 2 in front to balance those. 2 and 2. Let's do our last check. Na, oh, we kind of messed that one up for Na, so let's add a 2 here to make 2 and 2 for our sodium and 2 and 2 for our chlorine. All set. So because we're starting with one reactant and two or more products, this is a decomposition. There it is. D C2H6 plus O2 gives us CO2 and H2O. So when we see CO2 and H2O as our products, that should immediately signal this is a combustion reaction. Also, when we have a fuel with lots of C's and H's, and then it's mixing with oxygen, that's more evidence this is a combustion reaction. So I'll write combustion down here. And let's go ahead and balance. So remembering we might have to double it. 2 carbons, 1 carbon. Okay, so we'll double that guy. 6 hydrogens, carbon, 2 and 2. 6 hydrogens over here, and only 2 over here, so let's put a 3 to make that match. And now we can count up our oxygens. We have 2 here, and we have 4 plus 3 more makes 7. So we want to put something here that will give us a total of 7 oxygens, but this is in pairs, so that doesn't work out so well. We have to put 3.5 to give us 7 oxygens, and there's no such thing as half a molecule, so that's a 2. I swear it's a 2. No such thing as half a molecule, so we're going to have to double everything to get rid of that half. So we'll add that 1 in there just so that we can keep track of everything, and that 1 becomes a 2, 3.5 becomes a 7, 2 becomes a 4, and 3 becomes a 6. You'll notice there is no number that you can evenly divide into all of these, so it's still the simplest form. And we should have our numbers work out okay. So carbon, we have 4 over here and 4 over there. We have 12 hydrogens and 12 hydrogens. And now we have 14, 7 by 2 gives us 14 oxygens. And over here we have 8 plus 6, 14 oxygens. Okay. And last one, number 50. Write the balanced equation for this word equation. Silver nitrate. Here's silver nitrate from our periodic table, plus copper sulfite SO3 gives us silver sulfite SO3 and copper nitrate NO3. Okay, so notice I didn't balance or didn't form the right ionic compounds. Let's check all our charges. Silver is 1 plus, nitrate is 1 minus, so we're okay there. Copper, now we have to check the name to find out the charge of this copper because their periodic table won't clarify for us. So it says copper 2 sulfite, so this will be 2 plus. Sulfite, or sulfite rather, is 2 minus, so we're okay there as well. Silver, now we've got all the charges, you can just plug them in over here. So this is 1 plus, our sulfite is 2 minus, so we'll say Ag2SO3. And here our copper is still going to be 2 plus, it'll always be the same charge. And nitrate is 1 minus, so we're actually going to need 2 of these nitrates. My apologies for the bit of the mess there, but there you have it. So it says, write the balanced equation. So let's go ahead and balance our silver. There's 2 here and only 1 over here. So let's put a 2 to balance, 2 and 2. We have 1 times 2 gives us 2 nitrogens, 2. And over here we had 2 of these NO3 groups, so there's also 2 nitrogens. We're good. Oxygen is everywhere, so let's leave it to last. Copper. There's 1 and 1, so that's in balance. Sulfur, there's 1 and 1, so that's also in balance. And let's hope our oxygen worked out. So here's our oxygen, 3 of them times 2 gives us 6, and over here 3 more gives us 9. Here on this side, 3 plus 3 times 2 gives us 6 is 9. So 9 and 9 oxygens. So we are now balanced. Thank you for sticking with me. If you did, hopefully that was a useful exercise for you, and I'll look forward to seeing you for your test on Wednesday.